Okay, 3.4 inverse functions and relations. First, we're going to define what an inverse relation is. Two relations are inverse relations if and only if one relation contains the element AB whenever the other relation contains the element BA. Basically, what we need to get out of this is that x and y switch whenever we're finding an inverse. So the x coordinate of 1, which is the A term, now becomes the y coordinate. And the y coordinate of the first relation becomes the x coordinate in the second. So x becomes y becomes x. That is what we need to learn from inverses. That's how we find inverse relations algebraically. If we wanted to check to see if the inverse of a given graph or of a given function is a function, then we can use what's called the horizontal line test. If every horizontal line intersects the graph of a relation in at most one point, then the inverse of the relation is a function. So if we were given a graph and it did not pass the horizontal line test, then the inverse is not a function, even if the original is a function. A good example, which we can see here in the example, we're going to be looking at a quadratic. If we looked at a basic quadratic, scroll this down, y equals x squared. Well, basic quadratic is going to start at the origin, get a couple points here, 1, 1, 2, 4, negative 1, 1, negative 2, 4. Okay, that's the basic quadratic. Now that graph is a function, but clearly, you draw a horizontal line. That horizontal line hits the graph twice. So the inverse of that is not going to be a function. That's what the horizontal line test does for us. It just tells us if the inverse will be a function. Now we're also going to use this graph y equals x squared as part of our example. So let's go ahead and take a look at this example. Consider the function f of x equals x plus 3 quantity squared minus 5. Is the inverse of this function a function? Well, we know the inverse of a plane quadratic is not going to be a function because it doesn't pass the horizontal line test. Let's graph y equals the quantity x plus 3 squared minus 5. Now, I'd like to approach this with what we just learned with transformations. Okay, we have the basic graph x squared. Okay, we have some points. 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. And what we'd like to do now is look at what's the graph of y equals x plus 3 squared minus 5. All right, well, what does the 3 and the 5 do? The plus 3, the x plus 3, actually causes a shift to the left 3. Remember, whatever is inside, it does the opposite. It looks like we should go to the right 3. We're actually going to go left 3. Okay, so all of the points in x squared are going to be shifted to the left 3 and then down 5. That's what the minus 5 does here on the end. So I'm going to take all the points from x squared, move them left 3, down 5. So we'll start with 0, 0. Left 3, down 5. goes to negative 3, negative 5. 1, 1. Left 3. So it takes us to negative 2. Down 5, negative 4. Negative 2, negative 4. 2, 4. 2 minus 3 is negative 1. 4 minus 5 is negative 1. So negative 1, negative 1 here is that point. So we've graphed the right side of our parabola. Negative 1, 1. Negative 1 minus 3 is negative 4. And 1 minus 5 is negative 4. So negative 4, negative 4. And the last point, negative 2 minus 3 is negative 5. And 4 minus 5 is negative 1. So negative 5, negative 1. Okay, so that's the graph of y equals x plus 3 quantity squared minus 5. Is the inverse of this function going to be a function? The answer is no. We draw a horizontal line, and that horizontal line hits it more than once. So, is the inverse of f of x a function? No. We are now going to graph the inverse of f of x. Well, we just graphed the function y equals x plus 3 squared minus 5. Now we have to graph the inverse. Okay, remember, when graphing the inverse, x becomes y, y becomes x. So let's take a look at the points we currently have on this graph. I'm going to graph the inverse in color red. The point negative 5, negative 1. If I switch that, x becomes y, y becomes x. That point's now going to become negative 1, negative 5. Negative 4 stays. Negative 4, negative 4. Negative 3, negative 5 becomes negative 5, negative 3. Negative 2, negative 4 becomes negative 4, negative 2. And negative 1 switches to negative 1, negative 1. It stays where it's at. So, what we have, the inverse of f of x, or f to the negative 1 of x, that's our inverse notation, is in red. So the graph is basically a sideways parabola. Now what's an easy way to find that? Well, a simple way to find that is to simply reflect along the line y equals x. Now we talked about that before as a test of symmetry. Okay? You will find the inverse graph if you reflect a graph along the line y equals x. Now what we were doing with tests of symmetry was that if we got the exact same graph back, then it was symmetric with respect to the line y equals x. Now we are not getting the same graph back. What graph we are making, though, is the inverse of the original graph. So if we reflect across the line y equals x, that picture is the inverse of the original function, or of the original graph. So part A, the inverse is not a function. Clearly the red sideways parabola is not going to pass a vertical line test. And B, that is the graph of the inverse. How do we find the algebraic version of the inverse? Part C. Okay, so it's x plus 3 squared minus 5. F of x is the same thing as y. Now, when we graph the inverse, we simply switch the x coordinate with the y coordinate and the y coordinate with the x coordinate. Well, we do the same thing here. I'm going to write the inverse in blue. Y becomes x, x becomes y. The inverse, the equation in blue, is the inverse. That's it. Now, in order to put it in the right form, we need to get y by itself. We get y by itself, we can then replace y with the inverse notation. So, first step, we'll add 5. And now we have to get rid of a square. In order to get rid of a square, we will take the square root. So the square root of both sides. And if you take a square root and there is an equal sign involved, you must include a plus or minus. So this cancels out. Square cancels out. The square root cancels out the square. And then to get y by itself, we'll subtract 3. So the inverse function, or I should say, the inverse of f of x. Just because we use the f of x notation doesn't mean that it's a function. This simply represents the inverse notation. So the inverse of f of x is plus or minus the square root of x plus 5 minus 3. You also could put the 3 out front. There's nothing wrong with that. If you like negative 3 plus or minus the square root of x plus 5, that's perfectly fine as well. So to find the inverse, very simply, switch x and y. In other words, x becomes y, and y becomes x. Okay? Every x becomes a y, and every y becomes an x. Then solve for y, and you'll have the inverse of f of x. Now, we can look at the inverse graphs in our calculator if you want to confirm that with your calculator. Okay, here I have my graphing calculator. I'm going to graph the original, x plus 3 squared, plus, minus 5. So there's the graph. Now I need to get the inverse. There's two ways you can do that. First, algebraically we've done it. Okay, we found the equation. Plus or minus the square root of x plus 5 minus 3. So I'm going to put in the square root of x plus 5 minus 3 and negative the square root of x plus 5 minus 3. And there we can see the inverse graph. Or, let's say you don't know how to find this algebraically, and you want to see what the inverse looks like. Okay, we've typed in the original. We can now go to second program, which is draw. And if you scroll down, number 8 is draw inverse. So draw inverse of what? Well, of the original equation. That is y sub 1. That's our y1. How do we find that? Okay, vars, y vars, number 1 function. And we can pick y1. So we're going to draw the inverse of y1. If we hit enter, you can see it clearly drew the inverse. So even if you don't know how to find the inverse algebraically, you're having difficulty doing that, you should be able to still be able to draw the inverse with your calculator. Okay? And that is drawn by reflecting across the line y equals x. All right, that's all I have for today.